Every battery you've ever used, from the one in your phone to the one in your car, they all have a secret, a hidden flaw, really. It's something that decides how well it works, how long it's going to last, and, well, why it eventually dies. So let's go find this invisible saboteur that's hiding inside every single one of our batteries. And this secret? It's not totally hidden. It actually shows up in ways you've probably seen a bunch of times. Like, have you ever been in a car at night, you turn the key to start the engine, and for just a split second the headlights flicker and go dim? I'm sure you have. It's super common, right? But what's actually happening there? Well, that little flicker has a name. The culprit behind it all, it's something called internal resistance. That's the hidden flaw we're going to dig into. It's the reason for those dimming headlights, and as you're about to see, it's the reason for a whole lot more. But to really get a handle on this flaw, we first have to imagine what a perfect battery would look like. So, let's start with the basics. Say you need more juice than just one little battery cell can give you. Well, you've got to start connecting them together. But how you connect them, that changes everything. And to get why, we first have to talk about what a battery is trying to do in, a perfect world. Okay, so this perfect world potential, it has a fancy name, electromotive force, or just EMF for short. Think of it like this. EMF is the absolute maximum voltage a battery could possibly produce if nothing was pulling power from it. It's the number you see on the package, right? It's the battery's full on-paper potential, the absolute best-case scenario, before reality kicks in. So when it comes to combining these cells to get more power, you've really got two main options. On one side, you've got a series connection. That's where you link them up end to end, positive to negative, like a chain. And on the other side, you've got a parallel connection. That's where all the positive ends get hooked together and all the negative ends get hooked together. Okay, so why would you pick one over the other? Well, it really depends on what you're trying to do. If you connect batteries in series, it's like stacking them up. You add up their voltages to get a higher total EMF. Simple enough. But connecting them in parallel, that does something totally different, and for our story, way more interesting. It actually lowers that hidden flaw we've been talking about, the total internal resistance. And that brings us right to the main event. This is the big twist, the thing that separates the battery on paper from the one that's actually powering your phone. So let's properly introduce the villain of our story, internal resistance. So what exactly is this thing? Well, the simplest way to think about it is like friction, but inside the battery itself. See, the chemicals and materials making the electricity, they aren't 100% efficient. They create their own little bit of opposition, like a bottleneck that chokes the flow of current before it can even get out. It's like an energy tax that gets paid on the inside. And check out how Battery University frames this. They call internal resistance the gatekeeper. I mean, I love that analogy. It's so perfect, right? It's not some minor little flaw. It's the thing standing guard between all that stored energy and the device that needs it. It's the gatekeeper that, to a huge extent, decides how long your phone is actually going to run. And here's the real-world consequence, laid out plain and simple. That EMF, that's the perfect ideal voltage. But the second you plug something in and start drawing current, that internal resistance kicks in and causes a voltage drop. So the voltage you can actually measure at the terminals, what we call the terminal voltage, is what's left over. It's the ideal number minus that internal tax. All right, I know this might sound a little bit in the weeds, a little technical, but trust me, this one little factor, internal resistance, has a huge impact on how our modern gadgets work. You could even call it the silent killer of battery life. Let's look at how. You see, our modern digital devices are power-hungry in a very specific way. They're not like old analog tech that just sips power at a nice, steady rate. No way. Your phone, your laptop, they demand these huge, sudden spikes of current to run the processor or light up the screen. And it's exactly these massive power spikes where a high internal resistance becomes a total nightmare. And this chart, this data on some old cell phone batteries is just, wow, it's so revealing. Just look at the relationship here. You've got the nickel-cadmium battery, right? Super low internal resistance, 155 milliohms. And look, it gave a full 120 minutes of talk time. Now jump down to the nickel metal hydride battery. Its resistance is way, way higher, and it just failed the test. It couldn't deliver those power spikes the phone needed, even though the battery was still technically full of juice. So this is the key takeaway right here. This explains all those super frustrating things that happen with our phones as they get older. You know when your battery suddenly drops from 30% to 1%? Yeah, that's the voltage taking a nosedive under a heavy load, which tricks the low battery sensor. Or when your phone just dies, even though the meter said you had plenty of power left? That's because the energy is still in there. It's just stuck. It's trapped behind this huge wall of internal resistance, and it can't get out fast enough to keep your device running. Okay, so now we've met the villain. We understand how it works. Let's go all the way back to the beginning, back to that car in the dark and those dimming headlights. Because now, with everything we've learned, we can finally crack this case. It all breaks down into 3 pretty simple steps. Step 1. The starter motor in a car is an absolute beast. It needs a massive, massive burst of current to get that engine turning. Step 2. All that current has to flow through the battery's internal resistance, which causes an equally massive voltage drop inside the battery. And finally, step 3. With so much voltage being lost on the inside, the terminal voltage, the power that's actually available for everything else, just plummets for a second. And bam, the headlights dim. Mystery solved. So there it is. It's not some ghost in the machine or faulty wiring. It's a fundamental property of every single battery. This hidden gatekeeper, internal resistance, is the real key to understanding why some batteries work so much better than others, and why, in the end, they all fade away. And it really makes you think, doesn't it? I mean, if every battery we've ever used has this invisible flaw that's secretly calling the shots, what other hidden forces, what other kinds of internal resistances are quietly shaping all the other technology that we use and rely on every single day?